Before we dive into antenna types, it's probably a good idea to talk about something called polarization. Polarization is the orientation of the wave. If you think about signals as they travel through, through the air, most people think of them like this, that the signals go up and down. And for the most part, that's true. This is called vertical polarization. Oops. Now you hear the word polarization and polarity interchanged a lot, but that's actually not correct. Polarity is referring to like positive and negative. Polarization is the right word to use. Vertical polarization, the waves go up and down. They come out of an antenna. Say this is an antenna, it comes out up and down. Pretty standard. What's a little less known is horizontal polarization. Horizontal polarization, by the way, you cannot just do this. We'll probably get into that. But horizontal polarization is when the signal comes out of the antenna side to side. Now, this is much more difficult to draw because it would be sideways. But horizontal polarization is the signal goes side to side. Imagine this is like waves in a pond, and the side to side is like a snake in the desert. You can see that side to side motion. Now, what does this mean to us? Polarization is very important when you're talking about transmitting and receiving a signal. Let's give the extreme case. Outdoors. Let's say you have an antenna that is transmitting on vertical polarization. Now, by the way, in a lot of antennas, this is just how you mount it. Not omnidirectional, but like directional antennas, which we'll get into. If you mount it one way versus the other, you're changing its polarization relative to the ground. But let's just forget all that. All we're talking about is if you have vertical polarization transmitting this way, up and down, and your other side of your antenna is actually designed to receive it horizontally, so you're transmitting vertically, but you're receiving horizontally, that link will not work. That's how important polarization is. That the wave going up and down and trying to be received sideways, it actually won't hear it. There's actually a graphic that I've seen that if you look at two antennas, let's say you were to put these like this, two of them line up perfectly. So you see that the vertical goes into the vertical. Maybe I can demonstrate the other one with a different color here. We see the vertical goes to the vertical and all is well. But if we switch colors here, and let's say now we're going the vertical to the horizontal, you'll see that the vertical being in red, the horizontal antenna will only receive that amount. That's not a lot. So can you technically get a connection with one vertical and one horizontal? Yes, if there's enough signal strength, but it has to be a lot. There's like 30 decibels of loss. If you go back to your RF math, you remember 30 decibels is a ton. That is a lot of signal loss. So outdoor polarization is very important. And until recently, no one really thought of polarization as being important on the inside, indoors. And the reason is because of multipath. Signals bounce all over the place, so who really cares about polarization? That thought has changed. The reason is because the way we use our devices today. It used to be we would have a laptop, and that laptop would have antennas built right into the screen, and that's the way it was. It is, I would say. Those antennas are vertical in the screen, and our antennas on our access point are vertical. Now we have a polarization match. That's pretty good. But now we have these mobile devices. People are using them crazy ways, like vertical and horizontal and even flat. Now you're changing the polarization relationship between the transmitter and receiver. So the best systems out there actually are dual polarized. They have access points that can actually transmit and receive in multiple polarizations. It's not as easy to do as it sounds, but it is very important to do that. So hopefully that's a good understanding of polarization. Now let's get into the different antenna types. The first antenna type is omnidirectional. An omnidirectional antenna has a shape that looks like this. From the top, it will always be a circle. Now, one side note caveat here, there's never a perfect omni. if you look at any vendor, just pick a Wi-Fi vendor and you can look up their antenna charts, what their omnidirectional pattern looks like, you'll always see some sort of deviations in it. That's just because either, depending on multiple reasons, but it's very difficult to get a perfect omni. But for the sake of the discussion, anything from the top has a perfect circle of 360 degrees of similar coverage. The side view, okay, so we're talking, this is azimuth, this is elevation. The side view, may look something completely different. So an omnidirectional from the side may look like this. So it's taken that ball of dough and it's squished it. A higher gain omnidirectional antenna may do something like this. We've squished the dough even more. We're sending more signal out this way, giving us a bigger circle, bigger coverage area. But what's the downside of doing this? We could actually go to even show maybe something like this. Okay, this is a lower gain omnidirectional antenna. So which one of these is better? Well, none of them are better and none of them are worse. It depends on what you're doing. If I'm in a warehouse and my access point is really high, this lower gain antenna right here in black may be fine because I need some coverage down low and maybe some coverage up high. The blue may be a good compromise, maybe for an office building. Or maybe I'm outdoors and I'm on a tower or I'm on a location where I need to send the signal as far as I can in every direction. Now the red antenna would be right. So there's never one that's better than the other. Every antenna design is a compromise of another antenna design. So again, these are not better than, none of them are better than any others. It just depends on what you're trying to accomplish. But the key fact behind an omnidirectional antenna is that it's effectively a transmitting in a circle. The next is semi-directional. A semi-directional antenna, as you can imagine, is not omni. It's not transmitting in a circle. It may have a pattern, let's say the antenna's right here. It may have a pattern that looks something like that. This is your side view, your top view. Instead of the circle, like we showed before, the top view may look like this. So basically from the top and the side, they can almost be the same. That can be measured in degrees called beam width. You could actually, take this angle right here. We could say, oh, that's a 30-degree beam width antenna. And a lot of us talk that way, by the way. If we're saying, oh, hey, what's that antenna type? Oh, that's a 30-degree semi-directional antenna. Maybe we say patch, or maybe we say panel. We could say or sector antenna. We could say, oh, that's 30 degrees. Why is that important? Well, maybe I'm just trying to hit a stadium is a good idea. Maybe a good example. Maybe I'm transmitting from one area to the other, and I need to transmit to a certain set of people. That now with some math, we can actually see, well, will that 30 degrees, based on our distance, actually hit everybody we're trying to do? So that is a good example of why we need to know beam width. The cool thing is everybody publishes this. Every antenna manufacturer has some sort of guide or something that they use to publish that data that you can look at. So you can just look up what their beam width is. So these are, sorry, I should have wrote this, semi-directional antennas. There are multiple types. There are patch antennas, panel antennas, and even what's called a Yagi antenna. Let's at least write Yagi so you know how it's spelled. The Yagi antenna was the first one that I ever built. The one I discussed in another video is you have some sort of transmitter here. This is your node. And then you have these elements that go out with a central rod. Each of these elements are typically 1/4 wavelength from each other. Okay. I cannot encourage you to build this antenna. In some locations, that's not legal to build and use your own antenna, but it is always a fun experiment. You can go to your local hardware store, get a couple connectors off the internet, super cheap, and you can actually build your own if you are so inclined. So these are different types of semi-directional antennas. You'll see them physically, a lot of times they're square, different sizes for different gains. Larger antennas always have higher gains. Remember, a higher gain equals a lower beam width, so we can go farther, but we're compromising because we're squishing that dough. So these semi-directional antennas definitely have their use. But then we move into highly directional antennas. A highly directional antenna, as you can imagine, has a very tight beam width. So a highly directional antenna. Highly directional antenna could, we could look at it like this. Now, a lot of times these highly directional antennas are very easy to spot because they're some sort of a dish or a grid. Now, the difference between a dish and a grid, they're both curved and both have their transmitter that reflects that signal that one direction. The difference between a dish and a grid, dish tends to have less signal go behind it, called a backlobe. The backlobe is any signal that is transmitted behind an antenna that isn't really intentional. If it were a perfect world and it were possible, we would not have anything transmit behind it, but a lot it does. So that's called a backlobe. So dish antennas tend to have a smaller backlobe. The downside is they're more susceptible to being affected by the wind. A lot of times you'll see these plastic things over the top of a dish. That's because it's trying to make sure the wind doesn't affect it as much. A grid antenna looks kind of like a barbecue. In fact, if you're a super Wi-Fi geek, you could actually use it for one. It's curved, and it has these hash marks. It's basically just built just like you can imagine a barbecue. By the way, these are all in 1/4 wavelength of the frequency that antenna was designed for. So this grid or dish, now the grid upside is it doesn't get affected by the wind as much. It's actually really super cheap to produce, very inexpensive to do that. The beam pattern that you'll see, it can be very, very tight. Most of the time they are square, and what I mean by that is if my beam pattern looks like this, and let's say this is a 5-degree beam width on the side, on the elevation side, on the top, the azimuth side, it may also be 5 degrees. So I could just say, hey, this is almost identical, both top and side, both azimuth and elevation. That's what I call a square antenna. It's the same. Does that mean you can set it, just install it either way? No, remember that polarization thing. We may want the wave to go up and down, or we may want it to go side to side, depending on our application. The other type of antenna that's worth discussing is called a sector antenna. In my opinion, a sector is really not necessarily highly directional, but it's very different from a normal semi-directional antenna. So we're just talking about it here. A sector is designed to transmit only a specific number of degrees. Its beam width is is designed with that purpose. If you look at a cell phone tower, that's where you'll see sector antennas the most. If you look on the top down of these Roan towers, you'll actually see the antennas kind of look like this on here. 3 is not necessarily a magic number, but in Wi-Fi we use 3 a lot, especially in the outdoors because we had the channels 1, 6, and 11. We had 3 channels. So now that 5 gigahertz is more prevalent, that's not quite the case anymore. So each one of these would be 120 degrees, 120 degree sector. And then we would design that on the 3 channels, 1, 6, and 11. So now we have 3 access points. The end result is omnidirectional coverage, but you actually get a larger coverage circle, and you get more users because we have more access points and more channels that are being used. Now, we haven't got into that yet. You may not have looked at any videos talking about, what do different access points and channels really give me. But suffice it to say, that's the reason for a sector antenna. And these can get tighter. You could get 90s or 60s and then just start adding these up. The difference is cost, of course, versus how many users, how many devices, and how much gain you can get out of it. So that's a highly directional antenna. Let's talk about use cases for a moment. A lot of times people will talk about, let's say you have a short, let's say this is 1 mile. A semi-directional antenna, even a very low gain semi-directional antenna, could connect these two buildings. We'll say building A and building B. So we're trying to get data from building A to building B. It's a very common thing to do. What a lot of times is talked about is, oh, well, this is only a 1 mile shot. It does not need it doesn't need a highly directional antenna. A highly directional antenna could give you a 20-mile shot. As long as you can aim it right, it could do that. So is there a reason to ever use highly directional antennas in a short link? In my opinion, yes, and it should almost be your default thought. It depends on the location. If you're in a metropolitan area, you're trying to connect two buildings, there's a really important concept with antenna choices, and that is noise. An antenna is bidirectional. Whatever beam pattern you see here, it transmits in that beam pattern, which makes sense, but it also receives in that same pattern. Your ears receive better forward than they do backward. Now imagine if your ears had a 5-degree window in which it could hear. That'd be pretty nice. You would just point them away from the children and you wouldn't hear them as much. But look at this. If we choose a semi-directional antenna between these two locations, your beam pattern may look like that. Now remember, this is also 3-dimensional, so it's also to the side like that as well. And will that work? Absolutely. But look at what you're doing. You're actually creating excess signal that is not needed. You're sending your signal where it is not needed. Now, this is not a security play because you're encrypting your data anyway, but you're causing noise for other people and the vice versa. You're listening in areas where you could be listening to things that you don't need to listen to. Anything that you're receiving that is not intended for you is noise. It is causing you problems. So in these scenarios, I actually like to use highly directional antennas. I like to minimize my overlap, how much I'm transmitting and receiving, but now you can turn the power down. Because we have all this gain, we're actually going to get more signal than we need, which is also not good. But what we're trying to do is minimize the noise we hear and the noise we transmit. So if aesthetically, again, dishes are larger, they're kind of uglier than these semi-directional antennas, so this is all taken into consideration. But if you can use these highly directional antennas, turn the transmit power down, you can either do that with an attenuator, which is a physical device to reduce the power, or you can, inside of the transmitter, your access point or your bridge, you can actually reduce the transmit power. The end result is you're being more RF friendly. You're listening for less interference and you're transmitting less interference. And those two things, the end result is you get better throughput, you get better performance, and so does everyone else around you. So this was a long video. We talked about polarization, kind of an odd topic out there, but it's important to understand polarization when it comes to these antennas and antenna design. We talked about omni, goes everywhere, not as much gain. Semi-directional, covering just a portion of an area. A highly directional antenna like we've seen here. Patch antennas, panels, Yagis, just different types of antennas. Dish, grid, sectors, in order to, just different versions to achieve the same thing. Hopefully this worked out for you. This is a very important step. Next set of videos, we're going to go into, how do we use these and how do we calculate which antenna we need for our particular customer.